In this lecture, we want to talk about queue metrics or how to judge queues and waiting lines. There are five major measures that managers would use to evaluate and judge the performance of waiting lines. First is how many people are waiting in line. So that's the average number of people waiting in line or in the system. Second is the average time a customer would have to wait in line or in the system. Third is system utilization. Fourth is the implied cost of a given level of capacity and its related waiting line. And fifth is the probability that someone that would arrive right now would have to wait to get service. Here is a list of different performance measures that we have learned so far based on different characteristics of queues. So we're going to learn about these performance measures, then we're going to study and investigate different types of queues and measure their performances. Lambda here is customer arrival rate based on the idea that the arrival rate has a distribution, has a pattern, and it's going to be different. So lambda stands for the rate of arrival for customer. Mu, on the other hand, is for the service. So that's the service rate per server. L sub q, that's the length of L stands for length and Q stands for queue. That's the average number of customers waiting in a queue to get service. L sub S, on the other hand, stands for the average number of customers in the system. So Q is for the queue, S is for the system. R is the average number of customers being served. Rho, that is a Greek letter here, it's called rho. It's the system utilization. W sub Q is the average waiting time in queue. So that's the average time that customers have to wait in a queue. W sub S is the average time customers have to wait in the system. So Q is for queue, S is for the system again. 1 over mu is going to give us the service time. P0 is the probability of 0 units in the system, probability that there are 0 customers in the system. P sub n is the probability that there are n units or n customers in the system. And M, the capital M, is the number of servers or the number of channels. Liddell's law. What does Liddell's law tells us? It says for a stable system, the average number of customers in line or in the system is equal to the average customer arrival rate multiplied by the average time in the line or in the system, the average waiting time in the line or system. So using the notation that we learned before, we can write the Liddell's law as follows. L sub S is equal to lambda multiplied by W sub S. So L sub S is the number of people, the number of customers in the system, that's equal to lambda, the average arrival rate, multiplied by W sub S, which is the average waiting time in the system. On the other hand, we can write this also for Q. So L sub Q is equal to lambda multiplied by W sub Q. So that means the average number of customers waiting in the queue is equal to the arrival rate multiplied by the average time customers have to wait in the queue. We're going to use this Liddell's law in few examples to show you how to study different aspects of queues. Here we're going to study the queue performance of an MM1. A queue in which arrival distribution follows a Markovian distribution, for example, Poisson distribution, and the service time follows a Markovian distribution as well, such as exponential, and we have one server. So as you see in this example, we have one server here, and the first thing that we want to do about the performance is the average service utilization. Server utilization, which we show it by rho. So rho here, according to the formula that we have, is lambda divided by mu. So utilization means that how much of the server time or capacity is actually utilized. because it can happen that sometimes the server actually is idle. It doesn't, there is no customer to serve. So he or she is idle. The system is not being utilized. So that's that's actually important measure to study. So that's shown by rho, the average service utilization, which is lambda divided by mu. The next measure is the average number of customers in the queue, which in the formula we showed it by L sub Q. That's the average number of people who wait in the queue, not in the system. Because in the system, there are those people who wait in the queue and there are those people who are getting served. So L sub Q is the average number of people in the queue. And here is the formula for that. L sub Q, the average number of people waiting in queue, is lambda squared divided by mu multiplied by mu minus lambda. Next performance is the average number of customers in system. So that includes people who are waiting in line plus those who are getting served. That's the number of people in the system, L sub S. So that is, as shown in the formula here, is L sub Q, the number of people in line, plus lambda divided by mu, which is the number of people getting service, or the average server utilization. The next performance measure is the average time customers spend waiting in a queue, which we showed by W sub Q. So that's the average time that customers would have to spend on the queue. So that's equal to LQ divided by lambda, or if we actually use the formula for LQ, replace it here, we're going to get lambda divided by mu multiplied by mu minus lambda. So here we're actually using the Little's law in this formula. Next, we have the average time customer spend in the system, or W sub S. So the average time that people spend on the system would be the average time that they have to spend in queue, W sub Q, plus the service time. So that's what we have here. WS is WQ plus 1 over mu, which is service time. Next, we have the probability of 0 customers. What is the probability that there is no one in the system? That means the server is actually idle, it doesn't have to work for anyone. So we show it by P sub 0, and that's equal to 1 minus lambda over mu, which is 1 minus utilization. So, and it makes sense. Utilization, the whole time that it spends in a system, it's either is utilized or not utilized, which is idle time. So idle time and utilization has an inverse relationship, as we can imagine. And then we have the probability that there are at least n customers in the system. We show it by P sub n. P sub n is defined as lambda over mu, which is utilization, power n multiplied by the probability that there is no customer in the system. Now we're going to work on a series of examples for queue performances. Example 1. Suppose customers arrive at a bakery at an average rate of 18 customers per hour on weekday mornings. The arrival distribution can be described by a Poisson distribution with an average of 18 customers. Each clerk can serve a customer in an average of 3 minutes. So each 3 minutes, a customer can be served on average. This time can be described by an exponential distribution with an average of 3 minutes. The first part of problem, part A, asks for what are the arrival and service rate here, lambda and mu. So please pause here, try to solve this, find mu and alpha, and then come back to see the solution. All right, let's see the solution now. So to find lambda and mu, lambda is the arrival rate. So the problem says that it's a Poisson distribution. The arrival distribution is a Poisson distribution with an average of 18. So lambda is 18. On the other hand, for the service rate or service time, it says that it follows exponential distribution with an average of 3 minutes. That means that each 3 minutes a customer that is being served. So here we are talking for lambda arrival, we're talking about 18 customers per hour. So this means that we also have to use the same scale. So either we're going to work on hour for both, or we're going to work on minutes for both. So I'm going to keep the hour here for the arrival, and I'm going to convert the minutes for the exponential distribution of service time to hours as well. So each customer is going to take 3 minutes. That means that how many customers can we serve in an hour? So each hour is 60 minutes. This means that we can serve in 60 minutes. If you divide it by 3, it's 20. So this means mu actually is 20. 20 customers can be served in an hour. Part B of the question. Now that we know lambda and mu, the average arrival rate and the service rate, what is the average number of customers being served at any time? So please pause here, try to find the answer, and then come back to see the solution. All right, so let's see the solution. So the average number of customers being served, that's similar to the utilization. So that's actually lambda over mu. So that means at any given time, we have 18 over 20, which is less than 1. 0.9 customer. This is on average, of course. So at any given time, on average, 0.9 customers are being served. Here is part C of the question. Suppose it has been determined that the average number of customers waiting in line is 8.1. So that's L sub Q. It's given. Compute the average number of customers in the system waiting in line or being served. The average time customer wait in line and the average time in the system. So it's asked for L sub S, W sub Q, and W sub S. So please pause here, try to find these parameters, and then come back to see the solution. All right, let's see the solution. So here we have the formula. We know the average number of people in the system is equal to, that's LS, equal to LQ plus R. That's the average number of people in queue plus the average number of people being served. So we already have R, computed R previously in part B, and that was 0.9. And LQ sub Q is actually given here. That is actually 8.1. So L sub S is 0.9 plus 8.1 plus 9, which is 9. So L sub S, the average number of people in the system is 9. And as you see here, we can, based on having LQ, we can compute WQ as well. So W sub Q is the average waiting time in the queue. That's equal to, according to Ledel's law, it's equal to L sub Q over lambda. L sub Q is 8.1. 8.1 divided by lambda, which is 18. So that's equal to 0.45. 0.45 hour. You can convert this to minutes by multiply it to 60. And having W sub Q, the average waiting time in a queue, you can compute also W sub S. W sub S is WQ plus 1 over lambda, which is going to be 0.45 plus 1 over 20, which is 0.5 hours. Again, you can multiply these by 60 and get the average waiting time in minutes. Part D of the question, It asks for determining the system utilization when you have 1, 2, and 3 servers. So the formula is given here for utilization when you have multiple servers. That's rho equal to lambda divided by mu divided by m. So that's multiplied by m, as you see here. So just the difference that you have between this formula than the previously known formula, which was rho equal to lambda over mu. So this is for one server when m equal to 1, this m equal to 1. But when you have multiple server, then the formula become you have to include m, the number of server. So please pause here, use the formula and use the given information that you have had so far to compute the utilization of the system. All right, so let's see the solution. So we have lambda, we have m equal to 1, m equal to 2, m equal to 3, and we have mu, so we can compute these for when you have only one server. So m is 1, the utilization is 18 divided by 1 multiplied by 20. When m is 2, that's 18 divided by 2 multiplied by 20. And when m is 3, that's 18 divided by 3 multiplied by 20. So you can compute the utilization using this formula. Next example. An airline is planning to open a satellite ticket desk in a new shopping plaza, staffed by one ticket agent. It is estimated that requests for tickets and information will average 15 per hour, and requests will have a Poisson distribution. Service time is assumed to be exponentially distributed. Previous experience with similar satellite operations suggests that the average service time should average about 3 minutes per request. Determine each of the following. 1. Describe the queue system using Kendall's notation. So please pause here for a moment and write the notation for this problem using Kendall's notation, and then come back to see the solution. All right, so let's see the solution. So here we have the arrival time being Poisson distribution. The service time is exponentially distributed. So we have an MM system, and it says that there is only one agent, one ticket agent. So we have only one server here. There is no talk about the limitation on the queue size and population size. So we're going to leave that as infinite. So that's going to be an MM1 system. Let's see the second part of the question, the average arrival rate and service rate. So find or compute lambda, the average arrival rate, and service rate, which are lambda and mu. So please pause here, think about this question, and try to find lambda or compute lambda and mu. All right, so let's see the solution here. So we have the average arrival rate. The problem statement says that the average request per, it's going to be an average of 15 per hour. So that's 15 requests per hour. In an hour of time window, we get 15 requests. So lambda is 15. How about mu, the service rate? So we know that the service time is exponentially distributed. The previous experience with similar satellites says that the mean service time should be average about 3 minutes per request. That means that every 3 minutes, they can serve one customer. So we need to have the same time window that we use for arrival rate. So for arrival rate, we talked about hour. If we can serve a customer in 3 minutes, how many customers can we serve in an hour? So every hour is 60 minutes. 60 minutes divided by 3, we get 20. So in an hour, we can serve 20 customers. So mu is actually 20 here. Part 3 of the question asks for system utilization. So please pause here and using the formula and also given information that we have so far, compute the system utilization. All right, so let's see system utilization. System utilization, or which we show it by rho, is lambda divided by mu. We have lambda and mu, that's 15 and 20, so we can compute the system utilization. So system utilization is 75%. The fourth part of the question asks for computing the percentage of idle time that the server or the agent is idle. So compute that. We already computed the percentage of utilization, so we can compute the idle percentage of idle time by, that's going to be 1 minus the utilization rate. So that's 1 minus 75%, that's going to be 25%. So the system is 25% idle and 75% utilized. The fifth part of the question asks for computing the expected number of customers waiting to be served. So please pause, find the solution, and compute the expected number of customers, and then come back to see the solution. All right, so let's see the solution. So here we are asking for the expected number of customers waiting, not in the system, waiting. So that's L sub Q. And we write the formula L sub Q is equal to lambda squared divided by mu multiplied by mu minus lambda. So we have lambda as 15 and mu as 20, so we get 2.25. So the expected number of customers waiting to be served is on average 2.25. The sixth part of the question asks for computing the average time customers will spend in the system. So we're looking for average time in the system. That's W sub S. So please pause here for a moment and compute the W sub S and then come back to see the solution. So we have the formula for W sub S, that's L sub Q divided by lambda. So this would gives us the waiting time in the queue, and this would give us the time to serve. So in total, it's going to give us the time in the system, the average time in the system. So that would be 0.2 hour for 12 minutes. If you multiply this by 60 minutes, you're going to get 12 minutes. So the average time that customer will have to spend in the system is 12 minutes. The seventh part of the question is asking for to compute the probability of 0 customers. That's asked for P sub 0. Probability that there is 0 customer in the system, and also the probability that there are 4 customers at least in the system. So P sub 4 and P sub 0. So please pause here, use the formula to, and also the information and data that we have here to compute these two values, and then come back to see the solution. P sub 0 is 1 minus lambda over mu, and that's equal to 1 minus 75%, which is 25%. That's actually, if you remember, that's equal to the idle time. And that makes sense because when the system is idle, the percentage of the system is idle is actually when the amount of time or the percentage of time that there is no one in the system. So that's the probability that no one is in the system. And the probability that at least 4 people are in the system, we're going to use this formula, that's P sub 0 multiplied by lambda divided by mu power 4. And that's 0.079. So that's the probability that there are at least 4 people in the system. If you remember the definition of utilization of system and also the idle time, percentage of idle time, which complement each other, as a manager, you would like to increase utilization on the system, or on the other hand, you want to minimize the idle time in your system. But you have to be careful about what's going to happen in your system when you increase the utilization. So here is a graph that shows the system utilization versus the average number of customers waiting, or the average time waiting in a line. So as you see here, when you increase the utilization of system, as it increases, also the average customers that have to wait, and also the number of people that have to wait in the system, and also the average waiting time increases. So this is something to understand and be careful about, because it might have actually a drawback. You might actually lose some customers, and also it's going to be dissatisfaction among customers because no one likes waiting. Also, there's going to be the cost associated with waiting. We have studied and investigated waiting lines and queues from different angles and different aspects, mainly technicality and cost. But what should we not ignore is the psychology of waiting, because we are dealing with people and humans. So understanding the psychology of waiting is very important. If those waiting in a line have nothing to do to occupy their minds, what's going to happen is they often tend to focus on the fact that they are waiting in line. And it's going to make the unpleasant feeling of waiting in line more unpleasant. And also, they usually perceive the waiting time to be longer than it really is. So, knowing the psychology of waiting, we can take steps to make waiting more acceptable to customers. For example, we can occupy them while they wait. For example, you might have seen the in-flight snack, or the movies that they can watch in while they take a flight, or have them fill out forms while they wait, so you distract them from the fact that they are waiting, or make the waiting environment more comfortable or more appealing, or provide customers information concerning their wait. How much time have passed, for example, how longer they have to wait on average, or some other information that may help their feeling to understand that do not perceive the time as longer than it is. So taking these steps and similar steps can be helpful in reducing the negativity and the unpleasantness of waiting in line that would otherwise negatively impact your business.